Today we're going to discuss what we call complex circuits, or sometimes combination circuits. A complex circuit is one that is neither a series circuit or a parallel circuit, but instead some combination of the two. As you can see in the circuit that I've drawn here, resistor R1 and R2 are in series with each other because they're in a line, they form the same branch. The current through R1 has nowhere to go but through R2. On the other hand, R3 is not in series with R1 or R2. But R3 is also not in parallel with R1 or R2. So how do we go about discussing this kind of circuit? If you look at the two highlighted paths, the blue on the left and the green on the right, we can notice that while they are not the same branch, and so they don't necessarily have the same current as each other, they do have something in common. Notably, from one end of the blue branch to the other, from the junction where the blue branch starts to where it ends, it goes from the positive terminal of the battery to the negative terminal of the battery. We can say the same about the green path on the right. It starts at the positive terminal and it ends at the same potential as the negative terminal. In other words, the potential difference across R3 has to be the same as the potential difference across R1 and R2 combined. Because in the end, whether we go on the left path or on the right path, we're going from a common value of potential at the beginning in each case to a different but still common value of potential at the end of each branch. If we use the concept of equivalent resistance to redraw our circuit, we can actually see what's going on here. Having replaced resistors R1 and R2 with a single equivalent resistor, R1, R2, which is just equal to the sum of R1 and R2 because they are in series with each other, now we can see that the blue path on the left and the green path on the right are in parallel with each other. R3 is in parallel with the equivalent resistor R12 because both paths must have equal potential difference. There is only one resistor along each path, and so R3 and R12 are now in parallel with each other and in fact also in parallel with the battery. We can use this fact to redraw our circuit. Again, we can simplify it once more using equivalent resistance so that we only have a single resistor hooked up to our battery, where our single remaining resistor is the equivalent resistor of the entire circuit. In other words, the current through each of these three circuits through the battery is the same in all cases. The battery is being taxed equally by all three circuits, even though they're configured differently. If I had asked you in the beginning, what's the voltage across R1 or R2? Or what's the total current through this circuit? You might have not really had any idea how to begin. Once we redrew it like this on the top right, now you might have started to have an idea. But if I really want to actually find the current, this bottom right example makes it the easiest. I can find the current because I know that the current through the circuit using Ohm's law is going to be equal to the voltage provided by the battery divided by the resistance of the circuit, which is R123. Now, how do I find R123? I know how to find R12 because R1 and R2 are in series with each other, and series resistors simply add up. But I also actually know how to find R123 because R123 is the equivalent resistance of the resistor R12 that's in parallel with the resistor R3. And so I know how to find the equivalent resistance of parallel resistors. And then when I plug in R12, I find that the total equivalent resistance of our circuit is this. So now I know the total resistance of my circuit, given by this expression. I can also plug that in to find the total current used by this circuit. But if I want to figure out everything else, if I want to know the voltage across R3 and the current I3 and the current I1, which is the same as the current through R2, if I want to know the voltages across R1 and R2, the easiest way to approach this at this point is to make use of a VIR chart. I'm going to populate this VIR chart a little bit differently than before, though, because this time I'm going to include not just the resistors R1, R2, and R3, but I'm also going to include the equivalent resistor R1, R2, sort of to represent this branch as a whole. As before, the first thing we should do is populate it with the things that we start out with. In this case, as normal, although not necessarily as always, we start out with knowing each of the resistances and the total voltage of the battery. If the goal is to fill the entire VIR chart, in other words, to figure out everything there is to know about the circuit, then the usual approach is to look for the low-hanging fruit first. What is the information that we can figure out with the minimal amount of effort? Because the more information we have, the easier it will be to find the rest. So let's start with the easy stuff. First of all, we have already talked about the equivalent resistance of R12. We know that this is equal to the sum of R1 and R2. So we can write that down pretty easily. We also know that R3 is in parallel with the battery, which means resistor 3 is going to have the same voltage across it as the battery does. At this point, in the R3 row, we actually have some information. We have V and we have R, so we can figure out I is equal to V over R, and so the current through R3 is equal to the voltage of the battery divided by the resistance of R3. At this point, you'll notice that I don't really have any way of finding the voltages of R1 or R2 yet, nor the current through R1 or R2 yet. So that means I'm kind of stuck down here, but that's okay because I know how to fill in this last column. We actually already did this. This was the equivalent resistance of the circuit, as you see on the left, and so we know what that's equal to. Now we have two of the three variables in Ohm's law in the very last row, which means I can always find the current, which once again is the voltage of that row, which is the voltage of the battery, divided by, in this case, the total resistance of the circuit. So now what's the next step? Because that still hasn't populated anything in here. But if you think about it, the total current, which is the current through the battery, splits into I3 and I1, which is the same as I2. In other words, since I know the total current and I know I3, and I know that I3 plus the unknown current is the total current, I can actually write down these two currents. They're just equal to the total current minus the current through R3. Since R1 and R2 are in series with each other, their currents are the same, and since R1, R2 is sort of the merger of R1 and R2, the current through that is also the same. So I can extend this down. Now I have two of the three unknowns for my top three rows, which means I can find the voltages across R1, R2, and the voltage across R12, the equivalent resistor. This process of sort of chunking pieces of a more complicated circuit into, a series group, and then eventually a parallel group, and continuing to simplify the circuit using the concept of equivalent resistance is sufficient to analyze the majority of circuits. There are some where this method won't work and we have to fall back to just like solving the system of equations provided by loop rules and junction rules. But for the circuits that we're going to deal with in this class, this process is always going to be enough. For example, look at this awful mess of a circuit. I'm not going to actually go through and deal with all of this, but I do want to kind of qualitatively go through and address how we can work this out. So again, what we want to do is we want to identify parts of the circuit that we can describe as series or parallel, combine those parts, squish those parts into a single equivalent resistor, and continue that simplification process as we go. So first of all, these two can clearly be broken into a single resistor because they're in parallel with each other. These two resistors are also likewise in parallel with each other, so we can break them down into a single equivalent resistor. These two are in series with each other. These two are also in series with each other. So let's redraw the circuit based on that. I'm going to color code my resistors instead of naming them. I think most of that sort of chunking was fairly straightforward. This red bit might be a little bit confusing because there's so many connections here. But if you think about it, there is nothing but wire over here. So if I just care about the total behavior of my circuit, in the end, all of the current from these three are going to be split down these two paths, which I'm chunking down into one equivalent resistor. So the end of these two are at the same value of potential, and so are the ends of these three branches, the green, the yellow, and the one with the blue resistors, are all at the same value of potential, and that's true over here too. The right ends of these three branches and the left end of this resistor are all at the same value of potential. So I'm good there, although visually it might not be entirely obvious to you. At this point, we're almost done. I can chunk things a little bit more now. Along this bottom path, these two resistors are in series. And so I can redraw this circuit. I'm just going to replace the little bit here so I don't have to draw a whole new diagram. Now it looks like this. We have a single resistor here connected to three resistors in parallel, and then two more resistors in series. At this point, I only have two more chunks left. First of all, I can combine these three parallel resistors into series. And now I have four resistors in series, and so I can combine all those into a single equivalent resistor. And so my final circuit simply looks like this. And that's it, with some equivalent resistance. Obviously, I didn't do the math as I went, but along each step I can. Finding the equivalent resistance of two resistors in parallel is fairly straightforward. Finding the equivalent resistance of two resistors in parallel, again. Series is even easier than in parallel. And then in this circuit, we did one more series chunk in order to get this pink or purple resistor here. Then we combine these three resistances in parallel. Again, a little bit annoying, but not really hard. Then we're left with four resistors in series. We add them to get our final result. So that's 1, 2, 3, 4, 5, 6, 7 steps to arrive at our final equivalent resistor. So if you have a really complicated circuit, this process can certainly take a while, but it does allow you to boil things down until you're left with the simplest possible circuit that has the same current draw, the same overall sort of power usage and everything. One thing to keep in mind that I didn't mention before, but I should have. So in these videos, I have been using variables. I haven't been giving you numbers for resistors or currents or voltages or anything. When everything is in terms of variables, you just leave them as variables. In this unit, when we are dealing with Vir charts and loop rules and all that stuff, in order to make our lives easier, we leave out the units. And the reason for that is if I am constantly plugging in, like volts over ohms, and there's, over here it's an ohm plus an ohm, and then there's times ohms, and it can actually get really unwieldy. So what we do in this unit, again, only in this unit, is that as long as you always have your resistances in ohms, your currents in amps, and your voltages in volts, never millivolts, never milliamps, never kilo ohms or anything like that, just the standard base SI units of resistance, current, and voltage, then we just leave them out. And as long as you do all your multiplication and division of the numbers in these units correctly, the answers you get will also be in the corresponding unit. So for example, let's say my EMF is equal to 12 volts, a fairly standard amount. Let's say R1 is equal to 2 ohms, R2 is equal to 3 ohms, and R3 is equal to 3 ohms as well. Instead of plugging in to the equivalent resistance 2 ohms plus 3 ohms times 3 ohms divided by 2 ohms plus 3 ohms plus 3 ohms, I'm just going to plug in, 2 plus 3 times 3 divided by 2 plus 3 plus 3. In this case, it's, it doesn't really matter. Everything is resistances anyway. But when I start dealing with the more complicated things like voltage over R3 or voltage over R1, 2, 3 here, it's just easier to write this as 12 over blank and just leave out the units entirely. We can start to see up here with our currents, it becomes even a little bit more annoying. So my advice to you is when you're given numbers and you're plugging in a VIR chart, just make sure your units are expressed, your numbers, your values are expressed in the standard units with no prefixes or anything, and then just drop them and put them back in the end. It will make your life easier. Again, the reason we do this is because in this particular unit, there is a tendency for things to get out of hand, especially if we're dealing with, a bit of a more complicated circuit. And the whole point of units is they are significant, but as long as we are very careful about how we start going into a problem, we can put the units back at the end. And in this case, units will only make our lives harder. It just makes everything messier. And when you're dealing with so much information, messier becomes a problem. One last thing I do want to mention, because when I talked about parallel circuits, I realized that I actually left out something important about them. Consider a part of a circuit like this, where we have a 1 ohm and a 2 ohm resistor in parallel with each other. Well, the equivalent resistance of this circuit is going to be 1 ohm times 2 ohms divided by the sum, which will be 3 ohms, which gives us 2/3 of an ohm. And you'll notice that 2/3 of an ohm is actually less resistance than either one of the resistors here. This is very different from adding resistors in series. For example, if I have my 1 ohm and 2 ohm resistors in series, the equivalent resistance will be 3 ohms. So when you add resistors in series, they result in a bigger total resistance. When you add resistors in parallel, it actually reduces the resistance. This actually makes sense if you think about what resistance really means. Resistance is a measure of the impedance to current. Resistors impede the flow of current. They restrict the flow of current. Well, if I have, for example, if I cut out my 1 ohm resistor over here, if I remove it from my circuit, now the current can only flow this way, which means all the current being pushed through our circuit has to go this way. It's being forced through this one little resistor. If I put my 1 ohm resistor back, now the current doesn't all have to go through the 2 ohm resistor. It can split at this point, and some of it can take this path as well. And so by adding this other path, I've reduced the resistance to my circuit because now I've added another route for the current to take, so it doesn't all have to cram this way. If I add an additional resistor, even if it's a really, really huge amount of resistance, even if this is, a million ohms, it's still going to reduce the overall resistance of the circuit because this 1 million ohm resistance doesn't make it any harder for the current to flow down this path or this path. It simply means now the current coming in here from the left can flow through the 2 ohm resistor, the 1 ohm resistor, and there's a third path. Some of the current can go this way without obstructing the current through here. It won't be very much because this resistance is very large, but it will be some. And so by adding this third resistor, I'm going to increase the total current through my circuit, which means my equivalent resistance will have gone down. And generally speaking, or not just generally speaking, always speaking, the equivalent resistance of resistors in parallel will always be less than the smallest resistor that's connected in parallel. In this case, for example, if I get rid of my 1 million ohm resistor, I broke my circuit. The resistance is, as we saw before, 2/3. 2/3 is less than 2. It's also less than 1. And that's because I still have my 1 ohm resistor, so current can go through there, obstructed only by the 1 ohm resistor, but some of it can also go through this other resistor. Not as much maybe as goes through here because there's more resistance on the bottom path, but some will go through there. And that will reduce the resistance below what it originally was of just 1 ohm. So this is a good rule of thumb to consider with parallel circuits. Again, which is that the equivalent resistance of resistors in parallel will be less than the smallest resistor. You can think of this a lot like school, honestly. Consider some of the classrooms. Some of the classrooms in the building only have one door or one easily accessible door. At the end of class or at the beginning of class, when everyone is trying to enter or leave the room all at once, it's like a bottleneck, right? Only a couple people maybe or one person can fit through the door at a time. And so you have to funnel through one at a time. But now if there's another door open that also allows you to enter or leave the room, twice as many people can enter or leave the room at a time. One through one door, one through the other door. If instead of having a narrow door, if we make a wider door, a whole bunch of you could walk through side by side. And that allows a greater sort of current of students entering or leaving the room. If I put multiple of those doorways next to each other, that's kind of just like a bigger doorway. So it's less resistance to the flow of foot traffic. This analogy actually works very well. It works for series resistors as well. If there's just one door, when you're all trying to leave the class at once, and you're stuck at that door, you have to wait for the person in front of you to get out of the way. Well, once they're through the door, some people can go left, some people can go right, they can spread out and they can easily get away from the door, and there's no longer any kind of buildup outside of the door. On the other hand, if you have a classroom where there's a door, but the door leads to another door before you can finally actually get out, that's like having resistors in series with each other. You have to go through one door to get to the next door, and you can't spread out until after you get to the second door. And so the bottleneck will be longer, it's going to impede the flow of current over a greater distance, and it's going to create a bigger bottleneck. So understanding the qualitative behavior of the differences of series and parallel circuits can actually really be very well understood in terms of the dynamics of the mad rush of students trying to abandon a class all at once. One thing to be careful of, though, is when you don't just have a parallel circuit, but when you have resistors in parallel as part of a greater circuit. Here I'm using light bulbs because I think it's a little bit more demonstrative, and I want to assume that all the light bulbs are identical. So they all have the same resistance as each other. In this case, you have to be careful. Normally, I would say that in a parallel circuit, if I were to add an additional light bulb up here to this parallel branch, adding resistors or light bulbs in parallel to each other under the circumstances we discussed so far don't affect each other. If I have a circuit of 2 or more light bulbs in parallel connected to a battery, each of these light bulbs behaves independently of the others. Each one is provided the full voltage of the battery, and so each one draws a current equal to the battery's voltage divided by the resistance of the bulb, independent of the other bulbs that I add. Adding additional bulbs reduces the overall resistance of the circuit, like we just discussed. That causes more current to flow through the circuit, but that extra current simply flows into the new bulb that I added without affecting the ones that were previously there. In this complex circuit over here, that's no longer true, because you'll notice these bulbs, these parallel bulbs, are not in parallel with the battery. There is another light bulb in the way. And so when I add this third bulb up top, let me actually color code this. When I add this third bulb up top, that was thicker than I intended, but whatever. It results in the resistance of this part of the circuit going down. If the resistance of this branch, of this parallel part of our circuit goes down, that means because it's in series with the light bulb on the left, that means the overall resistance goes down. If the overall resistance goes down, that means the current through our circuit goes up. If the current through our circuit goes up, remember all of our current is coming out of our battery, which means all of our current is also going through this light bulb. If the current through this light bulb on the left here goes up, that implies that the voltage across this light bulb also goes up. And if the voltage of this light bulb goes up, that implies that the voltage across this parallel section of our circuit goes down, which means the voltage across these light bulbs goes down if I add another light bulb. So if I add lots and lots and lots of light bulbs here, what I'm doing is I'm decreasing the resistance of this part of the circuit, which allows more current to flow through the circuit. But all of that current passes through this light bulb, and so if the current goes up, this light bulb has a much greater voltage than it does before, again, because V equals IR, right? So if our current goes up and our resistance of our bulb stays the same, then the voltage across it goes up. And the voltage across this, if it goes up, leaves less of the battery's voltage for this because, again, from the loop rule, I know that the voltage across this light bulb plus the voltage across these light bulbs has to be equal to the voltage of our battery. So when you have a complex circuit like this, the idea that adding more elements in parallel doesn't really change what's going on with the other resistors in parallel no longer holds because of the interaction of this light bulb that's in series with the battery. So just bear that in mind. We can only say adding an additional light bulb in parallel has no effect on the currents through the other bulbs if it's a simple parallel circuit without any funny business of extra light bulbs attached in other ways. This should be enough to complete your next assignment. At this point, we've covered pretty much all of the foundations of circuits. We have one last little idea to talk about, which is the origin of resistance in a more like material property kind of way. We will probably do a little bit more practice with sort of conceptual analysis of circuits, kind of like what we just did here, thinking about what happens if I add a bulb there, what happens if I remove a bulb here, how is that going to change the brightness of the other bulbs, and so on. But at this point, we've really covered all of the foundations of this unit. All right, I think that's it, and I will see you next time.